Okay, let's talk a little bit more about the dot product and try to build some intuition about how this thing works, because it's a very important operation that's going to come up a lot for us. So one question you might ask is this. If I'm going to take the dot product between two vectors, I'm going to get a scalar back, right, as we know. One question that might occur to you is, what needs to be true in order for me to get a large dot product? Okay, what needs to be true about the vectors in order for the dot product to be big? And the first thing you might say is, well, if the entries in the vectors are big, then you're going to end up getting a big dot product, right? Because we're going to be multiplying each pair of elements between the two vectors and then adding them all up. So clearly, if the elements in the vectors are large, I'm going to get a large dot product, okay? That's true to a degree, but it's not the whole story, okay? And here's why. Let's take two vectors here. I'll call them x and y. I'm going to make x have 503 for its first element, and 297 for its second element. And then we'll say 0, 0, and then we'll say, something else big, 400, all right? And I've got my other vector y here, and we're going to say it's 0, and it's 0, and it's something big, 632, and then, 1 million, and then we'll say its fifth element isn't too big, we'll say that's 0, right? So a moment's thought will tell you why I'm doing this, right? This sort of extreme example, you can probably see that's the case, right? This isn't a large dot product at all, even though there are a lot of huge elements in there. And that's because, they're not big in the same places, right? Here we got 503 times 0. Here we've got 297 times 0. Here we've got 0 times 632, etc. So the fact that there's a bunch of really large elements in there doesn't really give us a large dot product unless they're large in the same places, right? Heck, I might as well have taken this vector, 1, 1, 1, 2, 1, and b 2, 3, 1, 0, 2. That's going to give us a bigger dot product than the first one, right? Even though all these elements are minuscule, we're going to get 2 plus 3 plus 1 plus 0 plus 2, whatever that works out to be, 3, 4, 5, 6, 7, 8, right? So 8. So this 8 beats this 0, even though there's some huge elements in x and y. Okay, so the lesson learned here is this, that when you do the dot product of two vectors, you're in some sense finding out how aligned they are, okay? How big they are in the same elements, because the only way you're going to get a large value for the dot product is if they're big in the same places, okay? So you may remember the example I did before where I was doing sort of a matchmaker.com thing, right? And I said, let's say that we give a survey to all the people on matchmaker.com, and Biff says, on a scale of 1 to 10, I like sardines, a 3, and I like, action movies, a 10, and I like bicycling on weekends, a 5, or whatever, right? And he answers all the stuff on the survey. And then maybe Kimberly and Jessica and Jezebel all answer, and they give different answers. And I asked, what is matchmaker.com going to recommend for a possible partner that guy would choose? And it's going to come down to essentially a dot product, right? The dot product is tailor-made for that, because if we say that our guy, I forget his name, Filbert, Biff, whatever. Let's say Filbert's vector is, I answered 3 on the first survey question, and then 10, and then 5, and then 0, and then 0, and then 9, right? He's going to come out a pretty good match for Kim if she says, 2, and I really like this, and this one's so-so, oh boy, I don't like that, hate this one here, oh, but I love that one, right? That's going to come out to be a pretty high dot product, because Filbert and Kim are pretty compatible. Whereas if I look at Jezebel here, maybe Jezebel has a lot of really large values, not there particularly, but there, oh my gosh, and there, oh my gosh, and there, and then not so much this one, right? I can tell you right now, just by glancing at it, that Filbert and Jezebel are going to have a pretty small dot product. And that's because they are not big in the same places, right? 10 and 0, 0 and 10, 0 and 10. Here's a 10 for Jezebel. It's only matched up with a 5 for Filbert, though, right? She's probably going to look better to a different guy. So bottom line is that that's really what dot product is doing for us. In some sense, it's figuring out the similarity of two different vectors. Now, it's not perfect that way because, again, you can overpower the similarity thing by being big everywhere, right? So Jezebel could say, if I have all 10s, then basically I'm going to be maximally compatible with every guy out there, right? Because no other girl is going to beat me in terms of being compatible with any guy. Because even if the guy has a 0 in a place, well, it doesn't hurt my dot product to have a 10 there, okay? So we'll learn a way to refine that in the next segment. There's a way to sort of level the playing field and make everybody even, which is called normalizing the vector, and we'll get to that in the next episode. But for right now, just think of the dot product as sort of a crude way of measuring how well two vectors are aligned, okay? Now, let me give you a little geometric lesson here, because this also is very, very illustrative. All right, so I'm going to draw some axes here. We're going to be dealing with 2 dimensions, because that's about all that human beings can handle, right? And I'm going to look at a few little pairs of vectors and have you think about what the dot product is, all right? So my first vectors here, I'm going to make that one, and I'm going to make that one. Okay, so vector number 1, I probably should do this in a different color. Let's do this in a different color. We'll make that one blue, right? Okay, so the red vector here is the vector 1, 0, and the blue vector here is 0, 1, right? And so in vector notation, we write it like this: 1, 0. Okay, so question: what is the dot product between these two? And obviously you can work it out, and the answer is 0. Okay, so the dot product of these two vectors is 0. Now, I'll do a second example. Let's say I've got a different 2 vectors. This time, my red vector is going to be 2, 2, and my blue vector is going to be -5, 5, right? So in our vector notation, we've got -5, 5, and we've got 2, 2. And my question is, what's the dot product? And you'll work this out and say, okay, 2 times -5 is -10, plus 5 times 2 is 10. Again, we get 0. Interesting. Okay, let me do one more case. Make my little axes here, my little tick marks. Sorry, this is so messy. Just kind of bad with this little pad here. All right, now for this trick, what I'm going to do is I'm going to say this guy is, oh, I meant to do that in red. We're going to say this one is the point -3, -1. Okay, so we're going 3 units to the left and then 1 unit down. And then for our blue vector, we're going to go down like this, and we're going to make this thing 2, -6. Okay, and so in our notation again, we've got 2, -6, and we've got -3, -1. Okay, so now we're going to multiply those together, do the dot product thing, right? So -3 times -2 is -6, plus -6 times -1 is 6. And lo and behold, we get a dot product again of 0. Okay, wow. So these 3 cases all gave us a dot product of 0. And now the big question, what do these 3 cases all have in common? And if you look at this, hopefully you'll have a spark of insight and you'll realize, I see what they all have in common. These are all at right angles to each other. Okay? All of these pairs in these examples are at right angles, 90-degree angles here. And the word you may have heard for that before is the word perpendicular. And it would be nice if we used that word in linear algebra. For whatever reason, we don't use that word. Instead, we use a synonym. And the synonym we're going to use, and this is the word you need to memorize, is the word orthogonal. And it does have a lot of O's. There's no A until the very end there. And orthogonal just means the same thing as perpendicular, which means the same thing as right angles, which means the same thing as 90 degrees. Okay, I don't know why mathematicians come up with a zillion different words for the same thing, but they do. Okay, so these are orthogonal vectors. Now, so the idea is that if 2 vectors are orthogonal to each other, perpendicular to each other, their dot product is 0. And that's because if you think about it, they are perfectly unaligned. In other words, there is nothing in common between the two. Okay? If I drew another example here and I said, okay, let's make it not so dire here. Let's say I've got my red vector going like this, and let's say I've got my blue vector going like this. Okay? Now they're certainly not in the same direction here, right? One's going northwards a lot more than the blue one is, right? But nevertheless, this angle is not 90 degrees. It's a lot less than 90 degrees, right? Let's say this is a 30-degree angle or something like that, right? So the way I think of it is this. If you wanted to go in the red direction, but you couldn't go in the red direction, you could only go in the blue direction, you would still make some progress redward, okay? You would still be able to kind of go in the red direction somewhat if you moved in the blue direction. Because in order to go in the red direction, we want to go north by northeast, right? And unfortunately, we can only go in the blue direction, so we have to sort of go due northeast, or maybe even a little east by northeast. But we're still going to get somewhat near where we wanted to go, because these vectors have something in common, right? Whereas if I had the green vector here, which was orthogonal to the blue vector, then I completely make no progress greenward if I moved in the blue direction. Because the blue direction is exactly opposite where the green direction goes. I'm completely moving in a nonsensical direction, which of course you can see better if we drew the axes like this, and these were our vectors, right? Let's say those were our vectors. It's pretty clear that if I move in the black direction here, I'm only going to go eastward. And even if I moved negative in the black direction, I'm only going westward, right? So by going in this guy's direction, I can only go due east or due west. There's no way to even get off the ground north and southwise. And that is because they are orthogonal to each other and have a zero dot product, okay? So one final thing to think about here, and again, we're very, very, very often going to deal with more than two dimensions, and so this whole geometric picture is going to kind of break down. But you want to sort of realize that in some higher dimension, it's still sort of the case that the two vectors are orthogonal to each other, and one is in a completely perpendicular direction to the other, and we can't get off the ground, right? Okay, so here's one last little fun fact. Let's say I've got two vectors here. Boy, my axes are ugly today. Okay, let's say I've got, we'll say this is our blue guy, and this is our red guy here, okay? And we want to know, what is the dot product between the red and the blue, right? Well, one way to compute the dot product is by, what we learned before. We can take, blue, which was, sort of maybe 5, 2, and we can take red, which is sort of maybe 2, 5, I don't know. And we can multiply this together and say that's 10 and that's 10, so the thing comes out to be 20, right? So another way we can do this, and it's kind of magic, but if you remember from your trigonometry what the cosine is of an angle, let's say the angle between these two things is theta. We'll just name it theta. That's a letter that's often used for angles here, right? Turns out that the dot product between these two is also, get this, the length of the red vector, and we're going to formalize that in the next segment, what we mean by length, but for now we just mean, Pythagorean theorem length, right? You can just figure out how long this vector is, okay? Times the length of the blue, times the cosine of the angle between them. Fun fact. And if you remember cosine, you'll remember that if you plot that, it looks like this. And importantly, the cosine is 1 when the angle is 0. And the cosine is 0 when the angle is 90 degrees. That right there is 90 degrees, or if you want to do it in radians, that's pi over 2, okay? Doesn't really matter. The point is that if the two vectors are orthogonal, the cosine of the angle between them is 0. And that is precisely aligned with our what we've talked about this segment and what that formula gives you, right? Because if the angle between them is 90 degrees, then the cosine is 0. It doesn't matter what the length of the vectors are. I don't care if you've got a million huge elements in your vector, Jezebel, and you've got a million huge elements in your vector, Biff. Your dot product is going to be 0 if the angle between you is going to be 90 degrees. And if the angle between you is 0, which means you're perfectly aligned, then the dot product is going to be the whole multiplication of the lengths of the two vectors. In other words, you don't lose anything by being off in terms of the angle between you. You are perfectly aligned if the angle between you is 0. Therefore, we're going to multiply by the maximum possible value for that cosine theta factor in there. Cosine theta is going to be 1 if you are perfectly aligned, if you have a 0 angle between you, and therefore that is when it's going to be at the maximum. So, bottom line is that the more closely two vectors are aligned in the same direction, where direction means something a little weird when we get to higher dimensions. It's much more, it's only possible to visualize really in 2 or 3. But when they're closely aligned, or when they're perfectly aligned, you get the maximum dot product. The further off they are, you get the smallest dot product.